previous two videos of this sequence, we defined the gravity field as the gradient of some scalar potential u, and we worked out that that scalar potential u as a function of distance from some mass m is just equal to gm over r. That applied for a point mass located at the origin. In this video, we'll take a look at how do we actually define this potential for a mass that has some arbitrary shape. So let's suppose that we have a lumpy mass here. Since we're working on gravity here, imagine this could be an asteroid or some sort of body that has variations in mass over it. And we'd like to get the scalar potential for a point at the origin due to this body here. So to do that, we can break this body up into a bunch of small infinitesimal masses, call them dm. And based on our definition of gravity potential, we can say that a small increment to the gravitational potential is just g dm over r, where r we get from, if this is our position vector of that piece of the body dm, then r here is the magnitude of this r vector. Now, to actually evaluate what the potential is, we need to turn this into an integral that we can actually evaluate. To do that, let's imagine that the density of this body varies as a function of position. So we have density rho is equal to rho as a function of r. And this is the r factor, so it's a function of the position vector. Now, if we are able to evaluate that at every point, we can say that the small piece of mass, dm, is equal to rho times the volume of this small piece, dv. So this is a little piece that is, say, dx by dy by dz. We would have seen something like this in a previous video on the divergence theorem when we looked at an infinitesimal cube. So this small piece has a volume of dv, and its mass is density times its volume. So we can rewrite this as g times rho dv over r. Now we have an integral that we can actually evaluate. We can say that u as a function of r is equal to the integral of g rho over r dv. And we assume that we have rho a priori as a function of position. It might be constant, it might vary, but we assume that we know it. And for every point, we can calculate what the value of r is. So we need to integrate this expression over the whole volume. Now, since in general we don't know what r is and we want to keep this solution as general as possible, we'll stop here for now. We'll just say that u is integral over some arbitrary volume. This whole thing has volume v. If we integrate the density, g times the density over r, over the whole volume, we'll get the gravitational potential at the origin of that whole body. So that's a useful concept. We can actually use that to define some other useful properties in gravitational theory. In the next video of this sequence, we'll take this expression and we'll see how we can apply this g derivation from u to actually get what is the gravitational field caused by this arbitrary body phi.